So we as developers, we've been spoiled by the once believed almighty monolith and its sort of single SQL database for way too long. It's a fairy tale world where we thought we could assume sort of strong consistency and one single globally consistent now. It was a world where we could like comfortably forget about our university classes on distributed systems. But knock knock, who's there? Reality. I mean, we have been living in an illusion, pretty far from reality, actually. I mean, today applications are deployed on, everything from mobile devices to large cloud computing clusters running thousands of machines, and each one of these, are usually multi-core now. So we are potentially deploying on like thousands of cores, and users are extremely demanding. They require close to 100% uptime. And if we don't live up to that, if the app is sluggish or you get downtime, they will go to competitor, right? So we can't sort of make the horse faster any longer. I think we need cars for where we're going to take the Ford analogy. And it's really time to wake up, and I think, and to retire the monolith. What we need to do is to decompose the monolith into like discrete services that each can be sort of managed in isolation, fail in isolation, be upgraded in isolation, et cetera, et cetera. And these services, they've had many names over the years. I mean, we have done sort of full circle yet another time as an industry. Now we call them microservices, and each time around we're getting a little bit better at it. I think. I mean, from core by sort of DCOM through SOA and now microservices. And the question is then, what makes them so popular now? And I was going to grab some water. Well, microservices can mean different things to different people. And they're usually driven by different goals and different requirements, etc. One way to look at it that is very popular, so this is about not a core, that's like canonical definition, it's just something I wrote up to capture this view, is that it supports multiple autonomous teams organized to scale the development, where teams can develop, deploy, and manage their services independently. This view takes sort of an organizational view, sort of around development and process, and it's one of the reasons actually why microservices has been so successful is that it's really good at that. It gives you a way to have each team being totally autonomous and deliver software independently of each other, and also enforces you to think about the protocols, the communication patterns between these, which is also a good thing, etc., etc. So that's all good. But today we're going to take a sort of slightly different look at microservices and put it in its perspective from an architecture and sort of development design perspective. We're going to try to put it in its true context, that is distributed systems. And in this context, then, how can we define a microservice? Yeah, one definition that captures the way I think about it is that it's a system of autonomous, collaborative, distributed services. And I've highlighted sort of system here and autonomous because I think that's two key aspects that I'm going to cover a little bit more in this talk. Of course, distributed as well, right? But I'm going to dive down a little bit more into what autonomous and system of services means. So autonomy comes from Greek, actually. I think it's pronounced AUTO-NOMOS. All right, I just asked my Greek colleague this morning, and then auto means self, and nomos means law. So it's sort of an entity that gives itself its own laws. In other words, two things: self-governance and independence. Okay, so being free from external influence. And researchers usually define it just in these two terms, being self-governed and independent. So that's sort of the definition that we're going to use here. And services, they need to be autonomous in order to take decisions independently and collaborate to solve problems, which is one of the things where microservices really shines, I think. And I mean, in my view, promise theory is sort of a theory created by Mark Burgess that I think is a great lens into microservices, because it really gives us a way of thinking about autonomous collaborative systems. It's sort of been it's a general theory that sort of explains how the world works, but I also think it's currently sort of taking off in the DevOps community quite a lot. No surprise, Mark Burgess, he was the author of CF Engine, and it's sort of been growing from within there. But I think it's a great way of thinking about distributed systems in general. So I'm just going to give you a short overview of what that is, right? Because I think it's really worth to dive into. You should read the book if you want to know more about it. It's actually a pretty short book. So we are used to thinking in terms of like impositions and obligations, like sometimes materialized through commands, and meaning that we tell someone what to do, right? We're letting one agent tell another what to do. And what's wrong with that? It's not always wrong, but one thing to keep in mind is that, and what promise theory teaches us, is that promises are local because you make them yourself, but obligations are distributed, meaning non-local. And according to the principle of autonomy, you only have control over local information that you own, okay? Which means that commands actually, and obligations and stuff, makes us lose control. And this leads to decreased certainty and stability in the system. So, promises, they express sort of the intent about an endpoint, where we want to end up, the ultimate outcome of something. And this is sort of independent of current status. And while this is very much different from commands or obligations, where sort of dictate what to do at a starting point, right? And that happens to be relative to where we are when we submit them. And convergence is a pattern, or is a common thing in physics. Like convergence can lead to a fixed point in the system. That means a stable point that you can't get out of, ideally. And divergence leads to system instability. So the interesting, the commands, so they sort of diverge from unpredictable into unpredictable outcomes from definite beginnings. So that means that you go from a certain state to an uncertain state, leading to decreased stability, while promises actually converge. They converge to a definite outcome from unpredictable beginnings, leading to increased certainty of the system and increased stability. And it's also important to understand that promises is of course not guarantees, right? There's no such thing as guarantees in a distributed system, or in any system, or actually in real life in general. So what does promises mean for an autonomous service? Yeah. It means that an autonomous service can only promise its own behavior in order to be fully autonomous. Okay? And embracing this really simple but sort of very profound fact has really huge impact in how we can design and understand collaborative systems. Because if a service can only promise its own behavior, then all information necessary to resolve a conflict, for example, receiving conflicting information or something like that from others, or repair under failure scenarios, etc., is available within the service itself. So removing the need for coordinating with others to get out of that state and to solve the problem. And autonomy leads to isolation, which is sort of the other important trait, I think, in microservice design. It's probably the most important trait. It sort of comes from autonomy, of course, but it's sort of the foundation for many of the other high-level benefits in microservices. And it's also the trait, I think, that has the biggest impact on your architecture and also on teams, etc. Because it will slice up both the organization and your architecture, So it will impact both the process as well as your architecture, etc. But this is a good thing, I think, in most of the cases. And this is just as Melvin Conway discovered in '68, and it was later turned into Conway's law, right? And I quote, "Organizations which design systems are constrained to produce designs which are copies of the communication structure of these organizations," right? And organization here and architecture, they go hand in hand. And isolation of failure, meaning being able to contain the failure without risking that it spreads through other components, cascading across your whole system, is a pattern often referred to as bulkheading. I'm sure you've heard of that. Right? And bulkheading is actually something that's been used in the ship construction industry for centuries as a way to divide the ship into watertight compartments. So if a few compartments are filled with water, the ship can still function, right, and reach its destination. And I guess, I mean, a lot of you might think, yeah, well, what about the Titanic, right? Yes, it had bulkheads. Yes, it did sink. A lot of people died. But actually, Titanic is a great example of bulkheading done wrong, because I mean, leading to cascading failure and catastrophic failure in the end, and thousands of people died. The reason was that these walls didn't go all the way up to the ceiling, so there were the compartments, they were actually not completely watertight. So when enough of the compartments were ripped up with water, the ship started to tilt and start to fill, the water started to be filled over to all of us, really leading to complete cascading failures. It's a prime example of cascading failure and what will happen in computer systems as well, I think. The resilience is really the ability to self-heal. And that requires compartmentalization, I mean, containment of failure. It also requires that we break free from synchronous communication, which introduces strong coupling, right, and causes instability in the system, right, when failures start to, spawn. So I really think that we need to embrace asynchronicity wherever possible. I mean, it's not a silver bullet. Sometimes you need synchronous communication, absolutely. But I strongly believe that if we don't know what we're reaching for, we should reach for synchronous communication. It's a great default, and then we can opt out if we really know what we're doing. Okay, so asynchronous means different things to different people as well. So some means I/O and some means communication. I think both are important and equally important to get right. I mean, async I/O is about sort of not blocking threads, that a process should not hold a thread hostage. Okay, while asynchronous communication is really about not blocking request, that a service that is processing requests should not block on another service and sort of impede progress. And asynchronous I/O, I mean, that means essentially asynchronous and non-blocking execution and I/O. I mean, it's most often a lot more cost efficient, right? Because you make more efficient use of resources that you don't, I mean, you give up resources that you currently don't use for others to use it, right? And this minimizes contention, which is the biggest like sort of blocker and hurdle towards scalability in the system. Right? Contention is evil and should really be avoided at all costs, right? So it also sort of puts a cap on scalability, low latency, and also availability. I think in the end, right? Because you can easily starve the system and stuff like that. So as an example, just to explain what I mean by asynchronous I/O. Let's say we have a service that needs to make like 10 different calls, right? Each one of these takes 100 milliseconds to do, and then it composes the result. With blocking I/O, these calls are sequenced. You can make one call, wait, then make one call, wait, one call, wait. So the total time in this sort of simplified example, I'm sure you can find holes in it, but just try to illustrate the point, is the combined time of 1 second roughly, plus perhaps composing the result. While if you use asynchronous dispatch, that means you can actually sort of dispatch all these out in parallel to these services, and the combined time will be sort of the longest request response time for one of these services plus the combined result. In this case, roughly 100 milliseconds. Asynchronous communication, as I said, is a service that's processing a request should not block on another service. And I think it's unfortunate that the sort of synchronous REST over HTTP is widely considered as the sort of go-to default service-to-service communication protocol. It's because, it introduces coupling between services. That sort of leads to a lot of bad things, including sort of adding a cap or putting a cap on scalability and availability, etc., and making the system more unstable and stuff like that. So I really believe that communication between services really need to be, as a default, be based on asynchronous communication. It's fine to use REST sometimes, absolutely, and it's fine to use synchronous communication sometimes. But if you do that, be aware of what you're doing, and try to put it outside the regular sort of request-response cycle, so it doesn't hold up things. Others shouldn't have to pay for that, essentially. And having an asynchronous boundary between services also allows us to decouple the services and their communication flow in two different axes. First, in time, and that is what enables things to run concurrently, and in space, which allows distribution and mobility, something that I will dive into more later. So, and perhaps more importantly, what asynchronous message passing does, it makes the constraints of distributed systems first class. Actually, the constraints of reality first class, really, without trying to fake it or hide, or, fake it until you break it, right? More than until you make it, I guess. And so, when in reactive systems, we talk about location transparency here. And that is the sort of, that we have one communication abstraction sort of across all dimensions of scale. So we have one unified programming model with unified semantics, right? Regardless how the application is being deployed, which topology it currently has, something that often actually does change. So instead of relying on different tools for each one of these dimensions of scale, like for example, you can use callbacks for interleaving on a single thread. Threads and locks across threads, like the regular Java style concurrency. Your message queues or RPC, across machines, etc. That just adds too much complexity. If you just embrace message passing at the essence of message passing, then you have one unified programming model that actually embraces all of these dimensions, that works across all these dimensions of scale, which is extremely powerful. And that instead of hiding behind the leaky abstraction that we have done way too much in the past, RPC or distributed objects, transactions, and stuff like that. So that's asynchronous communication. Now to something else. I really think that the word microservice is a terrible word. Okay? We should just avoid it. Because it implies size and makes people argue about the wrong things. What is the right size of a microservice? How big should it be? How many lines of code, etc. That's really irrelevant, and I think we need to stop this madness. It's really about one thing only. That is about scope of responsibility, adhering to the single responsibility principle. That's the old principle. I think Robert Martin stated in object-oriented design, but also that comes from Unix. That the right programs that do one thing and one thing well, right programs that work together. This fits very well. This philosophy fits very well in microservice design as well. The service should only have one single reason to change. There's also one way of looking at it. Okay? So because if a service has one reason to exist and providing a single composable piece of functionality, then business domains are not tangled, and it's easier to understand the system and to compose it and to maintain it over time, etc. Okay, but what about state? Sort of the elephant in the room here. I think what's needed is a microservice takes sole responsibility of its state and also the persistence of its state. And in a way, which storage medium is used for each individual microservice doesn't really matter. What matters is that each one is treated as a single unit. Okay? That it really owns its state completely exclusively, not allowing others to peek into your state, to looking up stuff in the database from the side, etc. Another thing is that ignoring the problem by calling the architecture stateless. By having sort of stateless services, then that's sort of pushing out the state in some sort of shared almighty database, will only delegate the problem. It makes it harder to control, and both in terms of data integrity guarantees, but also in terms of scalability and availability. It's better to take full control over the state and own the state, embrace it. And when designing these type of services, I think it's good to think in terms of consistency boundaries. Try to minimize the scope of this consistency boundary. And I usually try to think about. I usually don't start with the behavior, but actually start with the state. And think about how data interacts. As you see, so integrity guarantees from a domain perspective. Often talking to a domain expert about this. DDD can be a great help here. And then try to minimize the data set that has to be absolutely strongly consistent. And when you have that data set, then you add behavior. to that, and then you have your service. Then you really minimized the data set that needs to be strongly consistent. And I mean, trust me, you're better off that way. And as I said, DDD can help here. Bounded context is a great way of sort of thinking about this and sort of talk with domain experts about finding that the right size in terms of responsibility, scope for the service. And this also means that as I already hinted at, it doesn't matter which persistence medium you're actually using for each service. It can be different ones that are optimal for just that service that you're building right now. Some might use event logging, some might actually be better with the SQL database. Some might, use a time series database or whatever. And the beauty is that no one else needs to know, right? This is what we call polyglot persistence. Pat Helen said that the truth is in the log. A database is a cache of a subset of the log. And disk space used to be incredibly expensive. So that forced database implementers to reach for in-place updates, actually overwrite the existing state with a new, latest current state all the time. But today there's really no reason to use in-place update any longer. Disk space is extremely cheap. There's no reason to not keep history around forever. And so, why work with a cache of a subset when you can work with the real thing, the log? Actually, the log is the truth is in the log. So, I personally prefer event logging as a default for microservice design, or actually distributed system design in general. It doesn't always fit, but it's a good thing to reach for as the first thing, because it stores facts in order, in an event log, and the log is really sort of a database of the past up to the present, instead of just being a database of the present, like we're used to, and then we need to create a whole bunch of other tables to maintain history stuff, adding complexity for no reason, since the event log is actually there, it's called a transaction log in Oracle. It's just not exposed to us users, right? And a popular pattern for using event logging today is event sourcing, and that fits very well, I think, with a sort of a message-driven architecture, because you already have these messages flowing around representing either what you want to do or results, like facts. And it's very easy to just persist them to disk in order, and you have full traceability of what's happened in the system since day one. And this is often used together with CQRS, command query responsibility segregation, which allows you to use all the power of the event log, for the right side, but still store the state in an optimal format for reading on the read side. So it separates the right side from the read side, allowing you to use some great query language on the read side, while not having single writer principle and everything to minimize contention for the event log, which is really good. And finally, event logging avoids this sort of infamous object-relational impedance mismatch, which is also something that we've been struggling with for centuries now, or at least most of us since Hibernate, actually. So we don't need to install Hibernate any longer. This is nice. And so another thing that can be helpful is to separate the stateless behavior from the stateless part. The stateless part is usually called the entity, because that allows you to scale these independently of each other into different accesses. And scaling stateless behavior is easy. It can theoretically be scaled infinitely. Of course, there's the laws of physics doesn't allow that, but in theory. And it can be scaled in a very automatic fashion, just like, and we've seen that already, that was serverless, and Amazon Lambda is taking advantage of. And while scaling the stateful part is actually quite hard. One paper that can help you how you should think and frame that thinking is Pat Helen's excellent paper, Life Beyond Distributed Transactions. I encourage you to read that. I don't have time to dive into more about this, but read it. The final sort of trait for reactive microservices is that they need to be mobile, right? It's fully taking advantage of mobility. Mobility means the possibility to move services around while they are being used. And one requirement here is that services are addressable. You need this level of indirections. They need to be addressable through virtual addresses. And if you're used to writing programs in Erlang or Akka, then you know that you have a process ID in Erlang, the actor F in Akka, for example. And I think microservice design most does, but it's very important to take advantage of that, to take full advantage of the dynamicity that, for example, cloud computing gives you for elasticity, etc. So it's really paramount that the service is seen and moved around as a single unit, including behavior and state. And this just sort of to stay oblivious about the topology, which can and should actually change depending on the applications being used, ideally. So what is virtual addressing? Yes, I mean, and why would I've already explained what it is. I mean, but why would you need some? A few examples of why it can be needed is like load balancing between stateless services. I mean, stateless services allow you to send the request to any service, really. And you use different routing algorithms like round robin, you know, broadcast or load balanced or whatever. State replication between stateful services requires you often use something like sticky routing, that you actually route the request to the same service every single time, but still have like active in some replicas ready for failover if that happens. All that requires a level of indirection in order for the client to not really have to care about how that's being sort of handled behind the scenes. And then another thing is relocation of a stateful service. I mean, you might the runtime might need to actually relocate and move an instance over to its processing, to its main processing context, like closer to the data speed that it's using to optimize locality of reference, for example. All these things should be completely oblivious to the client. Reference should really always work. You know, even when a service is failing or being relocated or upgraded, etc. So, and this level of indirection in virtual addressing sort of allows seamless failover. And I mean, either to like a relocated instance or to a new replica that happens, or if everything fails, to a dead letter queue. I mean, so no messages are ever lost. So you have full traceability in the system. Okay, so now we're sitting here, you know, with all these new shiny microservices, so you should have a decent understanding, at least my view, of what sort of characterizes a single sort of reactive microservice. Okay, but one microservice is not of much use, right? In the spirit of Carl Hewitt, one microservice is no microservice. They do come in systems. And just like humans, I mean, they need to act autonomously, we already talked about there, and collaborate with others to solve problems. I mean, if they just do one thing and one thing well, then of course they need to collaborate in order to help each other to solve bigger problems. And it's also in the collaboration, you know, that both the most interesting problems sort of can be solved, but also that the most challenging things arise. You know, I mean, just as humans, I mean, it's in the communication with others that things can break down. And individual microservices, in my opinion, are fairly easy to kick off using things like Spring Boot, etc. You can very quickly, or Logom also allows you to do that. Just write like a single microservice quite easy, and spin it up. But what's hard in microservices, and then actually way too many, at least I say, I wouldn't say most, but way too many ignore is all the things around them. The interesting things is actually the space in between microservices. That's where all the hard things are. You know, things like discovery, coordination, security, replication, data consistency and failover, deployment, integration with other systems, etc., etc. And one of the main benefits of microservices is that it gives you a set of tools to exploit reality, really, to create a system that mimics closely how the world actually works. So, and that includes, of course, all these constraints and opportunities, so all in one package. And one of these constraints is that information has latency. I mean, it's a fact that information can't travel faster than the speed of light, and often travels actually considerably slower. But this means that communication of information has latency. So information is always from the past. We're always just looking into the past. And this also has the implication that the reality that we'll see is not consistent. really. There's really no single absolute present. So everything is relative, including time, and also our experience of now is relative. In a way, Newton was wrong with his absolute now. Einstein was right. They say everything is really relative to the perspective of the viewer. Okay? But we have been trying to maintain this illusion of a globally consistent now for way too long, I think. And the cost of maintaining this illusion is very, very high in most systems, right? It can be defined as two things: contention, there's waiting for shared resources, and coherency, meaning the delay for data to be consistent, the work that needs to be done for that to be consistent. And the first one is sort of normally represented by Amdahl's law. That is sort of the dotted line here. And Amdahl's law has its effect of that in a parallel system you can get diminishing returns when you add more resources to it, like more threads or more cores or something like that. Actually doesn't pay off as long. But even more interesting is actually Neil Gunter's universal scalability law that adds coherency into the picture. You know, the work that needs to be done to keep things in sync. In this, and according to the universal scalability law, you can actually start getting negative results when you start adding resources. So this cost of keeping, maintaining the illusion of a single global now, essentially, full strong consistency wherever, has a really high cost. And as latency gets higher, these solutions sort of breaks and cracks even more, because the difference between the present and the past is greater in a distributed system than in, of course, than in process in a local system. And as Pat Helen says, in a distributed system, you can know where the work is done, or you can know when the work is done, but you can never know both. You have to choose. That's a fact. So when we exit this boundary of the microservices into like this barren land, this unknown land, you know, we sort of outside the microservice, we enter a wild ocean of non-determinism. Right? That's the world of distributed systems. It's a scary world, you know, where systems can fail in the most spectacular and intricate ways, and where information gets lost, reordered, garbled, etc., etc., and where failure detection is nothing more than but a guessing game. It's scary stuff, you know. It might sound terrifying, but it's also the world that actually gives us solutions for resilience, elasticity, and availability, and all these things that are good, right? So it's something that we should reach for and learn to master. But it's also true that the microservice can be sort of an escape route from reality. Because within each microservice, we can still live on this like safe island, pretending that nothing has changed, and nothing can harm us. Like this safe island of determinism and strong consistency, an island that we can sort of live happily under the illusion that the time and the present is actually absolute, at least in our little world. And Pat Helland he defines a very nice framework, I think, for thinking about consistency, where he talks about inside data, on your little island, can be defined as the current local present. And outside data is what he called the blast from the past, that information always comes in from the past. And commands between services, sort of the impositions, sort of asking someone to do something, that's hope for the future. Hopefully it will get done. I think that's almost something poetic about that. We need to then try to really minimize coupling and communication, but because strong consistency sort of defines linearizability in distributed systems, requires coordination, which is extremely expensive in a distributed system. It really puts an upper bound, a ceiling on what we can achieve in terms of availability, scalability, and so on. And the need for coordination means that individual services can't make progress individually, but has to wait for others. Has to wait for consensus, right? And sometimes, as this like classic song, words are unnecessary, they can only do harm. We need to learn to enjoy the silence. And when designing a microservice, we therefore need to try to minimize the service-to-service communication and coordination of state. We need to learn to shut up, essentially. And as Bob Monkhouse says, like silence is not only golden, it's seldom misquoted. Can also like fits pretty well, I think. And as Pat Helen says again, The contents of messages are always from the past. They are never now. And I think exploiting reality means to coming to peace that information is actually always from the past. It's always representing another view of the world. So we're always, once again, looking into the past. And in order to model this, I think we have to rely on eventual consistency. And it's really nothing to be surprised about, because that's really how the world works. We're all experiencing eventual consistency all the time here. There's really no such thing as the one single global truth of information. So don't fight reality. Try to embrace it, and your life will become easier. It's also a fact, like, no one wants eventual consistency, really. But it's a necessary evil in many cases, I believe. Take everything I say with a grain of salt, right? It all depends. I might sound like I'm standing here being very opinionated, and I am, but I might be wrong as well in certain cases. I'm trying to just provide good defaults. That's all I'm trying to do. And in order to model this world, I think we need to learn to think in facts. Think and model the world in facts, and think about how facts are causally related. Because really understanding causality and how facts are causally related is a path to understanding how the system works. It's semantics. Semantics can be tried as the intent of the system, and it's dynamics, how it changes. So I love this tweet from Peter. And how do you do that? If you have a centralized sort of approach to it, then you can reach for event logging or a time series database or something that gives you this linear time, this ordering. If you can't do that, you can reach for, and you live in a distributed world, or has use cases that sort of requires distributed coordination or understanding. Then you can reach for vector clocks or CRDTs, conflict-free replicated data types, etc. But what is a fact, really? A fact represents something that happened in the past. And facts are values. That means they are immutable. They can't change. They represent something that have happened already. So, tough luck. You can't change that. You just have to accept that's a fact, okay? And how can, and facts, they only accrue, right? You can only build. You can only add new facts to the system, or you can sort of derive facts from existing facts. That's the two ways that facts can sort of enter a system. And I say we need to rely a lot on immutability here, I think. But I think mutable state, it has its place, right? But I think it only has its place if it's contained. It's only for local computations within the single service or something like that. So it's like within this sort of safe haven that is like non-observable to the rest of the world. And when you're ready with your local computation, then you can sort of publish the result as facts to the outside world to make it observable to the rest of the world. Okay, how you can communicate that out. So I think we really need to rely on facts. Another thing that's hard is protocol evolution. How can we manage protocol evolution? Because microservices are only independent if they can evolve independently, and this requires that the protocols and communication protocols are sort of permissive of change, because things will change and the protocols need to be evolved. And one good rule of thumb is John Postle's law here. Be conservative in what you do and be liberal in what you accept from others. And some of the challenges here is includes versioning of the protocol, upgrades or downgrades of the protocol, and some other non-trivial problem is like picking the right serialization codec, for example, that's extensible, that can be sort of upgraded, and maintaining some sort of data translation layer between protocols. And sort of actual almost versioning of the service itself, etc., like that, and things like that. And all these things can be put in what is called an anti-corruption layer. That's also a classic DDD pattern. And this anti-corruption layer can be added to the service itself, sort of as some sort of facade. But it can also be added in an API gateway, which is also something sort of common pattern in microservices design. API gateways are responsible for 5 things, like receiving the request, doing protocol translations if necessary, routing to other services, getting the replies, composing the replies, and sending back up to the client. And it really simplifies client to service communication. Instead of exposing like potentially tens or perhaps hundreds of services directly to the client, you can use an API gateway to simplify communication for it. So it just talks with the API gateway, tell it what to do at a more high level, and the API gateway sort of does all these hard things under the hood for you. Okay, that sort of make sure that you encapsulate the structure of the system even to the client, which can also be good because that means that you open up for possibility of change. Another thing is how can we manage complexity of communication? I think point-to-point communication can be okay if you just have a handful of services, but it can easily get into the complete incomprehensible mess of chatter. Beware, or your system will soon perhaps look like this. This is a sort of this is an image of a telephone tower in Stockholm, actually, and these are actually telephone lines coming into that tower, more than 5,000 ones. It's about 100-year-old. And I mean, if it starts to look like this, it might be a good idea to introduce some decoupling, to decouple it. I mean, using often some sort of pub subsystem, Kafka, Kinesis, or we're having through a NoSQL database like Cassandra or something like that. But you need to then break things apart and introduce a level of indirection to manage this complexity if you have hundreds or potentially thousands of services. Another hard thing is integrating with external systems. Like this really risky business. You're putting yourself at risk in the sort of, and you need to take precautions here, right? And synchronous communication, if you communicate with a service in a synchronous fashion, then you're really at the mercy of that system. Really, so we should really try to avoid that as much as possible and try to embrace, to really reach for asynchronous communication if possible. And if you can't do that, I mean, it also sort of depends on the communication protocol that the other systems are promises, opens up for. Then we need to protect ourselves, and one nice pattern for that is the classic circuit breaker pattern. That sort of allows you to sort of wrap the service and contain the failure if it happens, and having sort of exponential back-off policy with retries, etc. And you always need to apply back pressure, right? Or someone will definitely get hurt. And back pressure is really all about flow control. So what is flow control really? Yeah, it's about that a fast system should not be able to overload a slow system. I found this on Twitter yesterday. Yeah, that's definitely a need for back pressure, I think. So in order to get back pressure, you need to have this sort of continuous feedback channel. In this case, like where the fisherman can actually like to tell the fish to please slow down so I can catch you in a sort of in a decent fashion. And one great specification that implements that is, I'm sure you're aware of, is Reactive stream specification that a lot of libraries nowadays implement, right? Where there are implementations in Akka streams, Vertex, React, Oryx, Java, etc., etc. They are like reactive stream drivers for things like Kafka, Cassandra, and so on. So this really is something good to be aware of. You don't want to end up in this situation. It will take you down. Okay, but what about transactions then? Yeah, Pat Helen again is the hero of the day. He said, in general, application developers simply do not implement large-scale applications assuming distributed transactions. And two-phase commit is the anti-availability protocol. Short answer, you don't need them, okay? At least not as much as you think you do. So what should we do then if we can't reach for transactions? Grace Hopper once said it's easier to ask for forgiveness than it is to get permission. So what do we do, right? If we can't coordinate, and if we in real life can't be certain about something, what do? We usually take an educated guess that something that some premise or something a condition will hold, and if we're wrong, we apologize and we take a compensating action. And this is really sort of how the world works. This really matches reality very, very well. It's yet another time where we can exploit reality and embrace reality, and life will be simpler. Okay, because this is how we humans collaborate all the time, And other examples include, overbooking flights. I mean, I guess most of you, if you fly a lot, have been in a position that flights are overbooked, right? And then airlines try to like bribe themselves out of the problem by issuing vouchers, etc. That's the way you like sort of taking a bet that it won't be sold out. If it is, you apologize and perform a compensating action. Another example is ATMs. Like if the ATM can't connect back to the data center or mainframe, it still allows you to withdraw money, and then after the connection is restored, it will deduct it from your account, potentially to a negative balance if you're unlucky, if you didn't have the money, right? And but some people might say, but I really need transactions. Okay, let's say a practical and sort of scalable alternative to distributed transactions that sort of make use of some of the ideas that we've been talking about here is the saga pattern, sometimes called the process manager pattern as well. And it's a good alternative to XA transactions, I think. It's a way to managing this long-running transaction, often long-running business transactions, and it's based on the idea that you sort of divide this workflow into multiple steps, and in which the overall consistency of the whole transaction sort of can be achieved by sort of grouping these individual services in an overall distributed transaction. And if one of the stages fails, then it can kick off sort of a reversing action in each one of the states, so sort of a compensating action. It can be rolling back, but it can also be rolling forward into some other state. I mean, compensating the client in some way, or if you're out of stock, you perhaps put him on a waiting list or things like that. Performing some sort of compensating action when rolling back this business transaction. So that's pretty much all I had. I mean, to sum things up, I think we should embrace reality, and its constraints shall set us free, or something like that. Yeah. If you want to learn more, I wrote a very short report, or mini book, or e-book on this called Reactive Microservice Design or Architecture, and there's a link there you can download it for free. And in general, I mean, never stop reading. I mean, everything in this talk I've stolen from others. I don't think there's a single novel idea here, actually, which actually makes me proud because I mean, I will continue to keep on learning. These are some of the books that sort of influenced this talk. So that's all I had, guys. Thank you.